So as mentioned several times, rather than repeat what I did as we were going through all the different functional groups and just separate the A-level questions into functional groups, I'm separating them into concepts. And so we're starting off with a group of questions associated with what I call organic molecules. So we're not thinking about reactions at all. We're going to first of all look at physical properties of organic molecules and questions on them, and then questions on naming, questions on isomers, and so on. So crude oil, complex mixture of hydrocarbons, samples different locations, different fractions separated by fractional distillation. Why do the different fractions have different boiling temperatures? Well, they have different molar masses because you've got different numbers of carbon atoms, and hydrocarbons, you've got dispersion forces, and the more atoms you have in a molecule, the higher the dispersion forces, and so the higher the melting points and boiling points. So generally between similar molecules, melting point, boiling point increase with molar mass. Why is butanol soluble in water while 1-bromobutane is not? There's butanol, there's 1-bromobutane. You've got this OH here that can hydrogen bond with the water. Bromine has no hydrogen bonds with the water, and so water would be quite happy to see butanol, not very happy to see 1-bromobutane, because in order to dissolve the butanol, waters will break their hydrogen bonding to hydrogen bond with butanol, so no problem. However, they would be breaking hydrogen bonds to just form dipole-dipole interactions with the 1-bromobutane, not a very good alternative. Why does butanoic acid have a much higher boiling temperature than 1-bromobutane? Well, as butanoic acid, you've got, of course, capability of hydrogen bonding, not just with water, but with itself. Indeed, acids love to form dimers like this, and these hydrogen bonded dimers held together by 2 hydrogen bonds, much tougher to break than 1 hydrogen bond, which is much tougher to break than no hydrogen bonds. So butanoic acid, much higher boiling temperature because it can hydrogen bond, whereas bromobutane, all it has is dipole forces. 2 students each given alcohol. They added the alcohol to a separating funnel with water. This is what a separating funnel really looks like. The pictures that I'll show you in a minute, pretty ugly. Shook the mixture, let it stand. Here's the diagram. So here's the ugly separating funnel for student A, ugly separating funnel for student B. Student A has 2 beautiful layers indicating the alcohol is not miscible. Water will be the lower layer, alcohol will be the top layer. On the other hand, student B's only 1 layer, indicating that the alcohol and the water are miscible. If it's insoluble, alcohols have OH, so they can all hydrogen bond to water, but if there's a huge big hydrocarbon chunk in the rest of the molecule, well then there's so much hydrocarbon there repelling the waters that the fact that some waters can pop in on the end and hydrogen bond with the OH doesn't really help. That usually happens when you've got alcohols greater than 6 carbons. On the other hand, student B's alcohol miscible with water. That means that the hydrocarbon bit, while it's there, is not so extensive that it overcomes the nice positive effect of having the hydrogen bond between alcohol and water, which it is, depends on how much alcohol water was used. Methanol, ethanol, and propanols are completely miscible with water, so it doesn't matter the ratio. However, butanol, pentanol, hexanol have got limits in the amount that you can mix, so it really does depend on how much alcohol to water you had. But to have it totally miscible, you probably say less than 4 carbons. So why is ethanol soluble in water, ethane not? There's ethanol, can hydrogen bond to water, so therefore when you add it in, the delta H of the solution will be close to 0 because you're breaking hydrogen bonds between the water molecules, but you're making new hydrogen bonds to the ethanol. Ethane, on the other hand, CH3, can't hydrogen bond. It only has London dispersion forces when it's pure ethane. When you put it in with water, the best that you can get is the dipole of water to induced dipole of the ethane, which are pretty weak forces, so therefore you're breaking nice strong hydrogen bonds, replacing with weak dipole induced dipole, and so the delta H is solution very endothermic, so is not going to happen. Ethoxyethane, much lower boiling temperature than ethanol because molecules can't hydrogen bond for each other. What does a molecule have to have for hydrogen bonding to occur? Well, hydrogen bonded to an atom X, where X is electronegative, so it's a nice polar bond, but it's not enough that X is just electronegative. It needs to be electronegative, very electronegative and small. And the atoms that fulfill that are the fluorine, oxygen and nitrogen. Most electronegative, second most electronegative, fourth most electronegative. Chlorine isn't in here, the third most electronegative because it's not small, as these are all second shell atoms. Chlorine is a third shell atom. And of course, when you got that, there's the hydrogen bond, the slightly positive hydrogen in one molecule, interacting very fiercely and strongly with the slightly negative end of another molecule. Comparing propanoic acid and hexanoic acid. When we look at these, we first of all see that really leaps out, both of them have acid groups. Okay, those acid groups can hydrogen bond. They can hydrogen bond with themselves. They can hydrogen bond with water. And then the rest of the molecule in gold here is the hydrocarbon bond, which has dispersion forces. Now, dispersion forces can bond quite nicely with themselves. If you have two hexanoic acids next to each other, you can have this hydrocarbon chain quite happily interacting via dispersion forces with another hydrocarbon chain. But water hates hydrocarbon chains, so these dispersion forces part bad for interacting with water. Now, when we think about just comparing them, both of them have the same hydrogen bonding capability, but hexanoic acid is going to have a lot more dispersion than the propanoic acid. So that means that propanoic acid will be more soluble in water because it has less dispersion, but the hexanoic acid will have a higher boiling point, same hydrogen bonding capability, but more dispersion, higher molar mass, therefore higher boiling point. 2-aminoethanol, colors liquid, soluble in water, ability to hydrogen bond with water molecules. Complete the diagram to show that hydrogen bonding. So let's make it bigger and bring in the lone pairs. Put in the fact that the nitrogen and the oxygen are nice and electronegative, so therefore they will be forming polar bonds to the hydrogens, where the nitrogen and the oxygen are the slightly negative ends and the hydrogens the slightly positive ends. And of course, slightly negative, slightly positive bits are very important for showing the hydrogen bonding. So let's bring in water molecules towards this molecule. Here's a water molecule coming in, leading with the slightly negative oxygen. Slightly negatives like slightly positives, so there's a hydrogen bond feasible between a water molecule's oxygen and the hydrogen of the amine. I could also have drawn it so that there's a different water molecule hydrogen bonding to this hydrogen of the amine, but I don't want to clutter it up too much. Water doesn't just have to come in oxygen first on this end of the molecule, it can come in oxygen first on this end so that the oxygen of the water can form a hydrogen bond with the hydrogen of the alcohol group. Then, of course, water not only has slightly negative oxygens, it has slightly positive hydrogens. So the slightly positive hydrogens of a water molecule can interact with the slightly negative nitrogen, as shown there, or with the slightly negative oxygen of that end. So overall, we have all kinds of hydrogen possibilities. We've got 1, 2, 3 hydrogens that can act as hydrogen bonding donors. And then, of course, we have the lone pairs 1, 2, 3 that can act as hydrogen bonding acceptors. Now we're comparing our 1,2-diamino ethane, which is this molecule here, with our 2-aminoethanol right there. Okay, the 1,2-diamino ethane has a boiling temperature of 117. The 2-aminoethanol has a boiling temperature of 170. Okay, why such a big difference? Because let's face it, you've got hydrogen bonding here, and we've got hydrogen bonding capability here, which I've just drawn nice and quickly. Looks like exactly the same hydrogen bonding pattern. Indeed, you could argue that here, this hydrogen here can go off on another water molecule that this one doesn't have that capability of. But let's compare the hydrogen bonding, shall we? Okay, because the amine end is the same in both cases, but now we're replacing or comparing a alcohol group here to an amine group there. Okay, and seeing as how these are the differences between the molecules, that must be what gives rise to the difference in the boiling temperature. So what's different between hydrogen bonding via an oxygen and hydrogen bonding via a nitrogen? Well, as it turns out, quite a few. Hydrogen bonds to oxygen are stronger than the hydrogen bonds to nitrogen. So in other words, these hydrogen bonds here are better than those hydrogen bonds there. Why? Because oxygen is much more electronegative than nitrogen. Seeing as how hydrogen bondings rely on polar bonds arise as a result of electronegativity differences. Seeing as oxygen is more electronegative than nitrogen, these hydrogen bonds will be better than those hydrogen bonds. So looking at some esters here, all of these esters have the same ethanoate acid part, so they all came from ethanoic acid, but then they have different R groups. In other words, the alcohols were different, and what we see is that they're all isomers, these R groups. They all have 5 carbons and 11 hydrogens there, but different structures, either 2-methylbutyl, 3-methylbutyl, or the straight chain pentyl ethanoate. And we're given the boiling temperatures. Now, of course, different boiling temperatures arise because you have different intermolecular forces. If we look at all of these esters, we've got 2 distinct parts of the ester. You've got the ester group there, the methyl, and then there's slightly negative oxygen there, and there's slightly negative oxygen there. That's the polar part of the molecule, but that's the same in all of them. Okay, so that's not going to contribute to the differences in the boiling temperatures. Now, what must therefore contribute to these differences is the R group. Now we're asked to compare between A and C. Both of these R groups are just hydrogen bonding, which means all they have between them are dispersion forces. But why are the dispersion forces sufficiently different that we have a 13-degree difference in boiling temperature? And the answer is, if we just think about just those dispersion forces. Here's the pentyl group. Okay, it can line up quite nicely and quite closely to other pentyl groups compared to the 2-methylbutyl group here, which of course they've got these branches sticking out, therefore the groups can't get as close to each other, therefore the dispersion forces will be weaker. Okay, so if the dispersion forces are weaker in the 2-methyl ethanoate, that means the boiling point will be less.